Yeah. He's chosen to try and to Fairbanks. They're very reluctant in taking it. Yeah. Cool. Is it time? Oh, for this? Oh, okay. Okay. There you go. Thumbs up from tech support.
Hi everyone, thanks for coming. Today we have Philip Hayes, our own mechanical engineering graduate. He graduated from our department, from mechanical engineering department in 2017, if I'm not mistaken, and he is an engineer with Alyeska Pipelines. So I will give the podium to Philip Hayes.
Right, there we go. To get to mentioned, I graduated here with my master's degree in 2017. I also got my bachelor's from University of Alaska Anchorage. So they're starting to call me student emeritus here. I've just kind of been going along so long. So we're talking about seasonal thermal energy storage. A little bit of background about why that interests me is over 40% of all residential energy usage is to space heating. That equates to $73 billion a year. Oh, it's on autopilot, sorry. So for me personally, that's $162 a month with my level pay with NSTAR, and it also is 324 million tons of CO2 generated in the United States specifically. Well, except for me, that's Anchorage, Alaska specifically. So real quick, we're going to go through the existing thermal energy storage systems test design standards and how those equate. Most of those are going to be from ASHRAE handbooks. Then I'll talk a little bit about my research for my master's degree and how that relates to the design standards. And quickly go over the results and current research that's happening in this field. And so again, primarily from ASHRAE standards, and this is a thermal energy system that ASHRAE kind of thinks about when they think about their thermal energy systems. You have a large thermal energy storage tank that's going to be holding whatever your heating medium storage is going to be. If there's a demand for cooling, it'll come through, run through your appliances, reject heat into the fluid, send it back into the storage tank. What's really nice about this, and they have a lot of information on designing this, is it takes advantage of stratification in the water. So you'll have your design high temp and your design low temp thermocline, and that'll adjust either daily or if you have a big enough tank seasonally as well. So that's a nice way to optimize efficiency. ASHRAE says thermal energy storage system is simply a system that stores thermal energy in a medium for use at a different time. It's one of those self-defining terms there. So there's several types. Passive, I generally don't recommend it. Maybe it's because I'm an engineer and I like control of things. It's nice, but you'll see these systems, large windows, large thermal masses, pools, architectural concrete. Again, the best window money can buy is still not as good as a 2x4 insulated wall. So unless that's changed, somebody knows a really awesome new window. So generally windows from a heating perspective and cooling as well are not preferred. And an active system, that's defined as pumps and fans move your fluid from your heat source to your heat storage medium. And simply put, hybrid is any combination of those. So hybrid, a good example of a hybrid system would be like a greenhouse. So you just kind of pump it into the floor of the greenhouse, let it radiate into the environment. Nobody's going to really care if it gets too hot or too cold in there, but where human occupancy comfort is a concern, as defined by ASHRAE Standard 55, it's hard to meet those standards when you're dealing with any system but an active system. So, per ASHRAE Standards 2016, Systems and Equipment, they list the advantages of having a thermal energy storage system. You can reduce your initial or operating cost. So if you're designing a system And you're like, fudge, that brought me right into a engineered to fit system instead of an off-the-shelf system. You can typically size a daily system to come down off that initial cost. And of course, your operating costs, long-term, smaller system, easier to maintain. And then, just real quick here, there we go. Peak load, not much of a concern for residential. I don't have much experience commercially with peak load, other than they say, don't bust our peak load. That's too much money, just don't bust it. Whatever you can do, don't bust it. That's my experience with commercial peak load. So I don't know how that pricing matrix, it was explained to me as goofy math, but that's more accounting than engineering, I think. So also backup capacity for those who have infrequent supply. And then if you want to extend the capacity of your existing system, thermal energy storage can do that. And they help. The big one, especially focusing on residential, is a lot of people want to be off the grid. They want to reduce how much grid energy they take via, be it cost-wise or just you want to kind of be a doomsday prepper guy. So an ASHRAE, like every code book I read, says for a properly designed and installed system. So it says, here's some guidelines, but you can't do bad engineering and you can't do bad installation. Don't blame us if it doesn't work. So for the ASHRAE guidelines, this is kind of the system that they're talking about when they talk about it. You'll have a large heat generator, in this case solar collectors, to a large reservoir where it's stored for seasonal use, and then you have your end users. So coming through pretty quick for their design applications, they recommend for residential to have a central solar heating plant with seasonal storage. They go a little crazy with the acronyms. Sorry if kind of keep up, because I know we all come from different industries that have our huge acronym pools to draw from, so it becomes quite a bit of alphabet soup there. They assume a large natural reservoir, and they also kind of go off flat plate solar collectors. This is the predominant usage in. And they explicitly, they used to say not recommended for small scale residential design. The latest update says design with care, it may be cost prohibitive. And water being the medium of both heat transfer and storage. And the one that I love is again, they used to say don't recommend, now they say take special care when designing for systems with extended freezing periods. So that just kind of says Alaska, too bad, right? It's going to be too tough for you. So that's their recommendations, and for how the actual getting down to the designing of the system, they kind of say find an aquifer, and they think they meant confined aquifer. So when you have a large system, a natural water reservoir to reject heat into, water, it's great for heat transfer. You can transfer a lot of heat. You can store a lot of heat into it. So it's right at the top. They're like, hey, if you can find aquifer, that's great. For cooling or heat pump applications, it's not really thermal storage. You have an unconfined aquifer. So you have just constant moving water. You have an infinite temperature source. So you don't really need solar thermal at that point. It becomes an ideal ground source heat pump kind of installation. So, and they also recommend you size the seasonal system only to take 50 to 80% of the load. That's because our seasons get tricky. They say, hey, here, design to an average season, but now we're going to have a heat wave where we hit 80 degrees in Anchorage, or have a cold snap where we get down to minus 25. So that lends us to say this is going to be a supplemental system. You'll still have, or if you wanted to design it to be your primary, it'll become, you'll have another supplemental system to take those extremes that happen normally. And this is their current guideline. It is a little over 2 to a little over 3 square feet of collector per square foot of floor area. So that becomes quite a lot of collector space. And then they recommend 10 degree delta T or greater. The greater the heat transfer, the better your heat exchanger and all those efficiency numbers. So they're saying if you're not going to be able to get 10 between your source and your storage, you're not hitting efficiency numbers to make it effective. And then they recommend 70 cubic feet of water equivalent per a unit collector area. So you have 2 square feet of collector area, you have 140 cubic feet of water storage. And you see these systems can get pretty big, pretty quick, and that goes back to why they recommend not for small scale residential use. These systems are applicable commercial, industrial, that current standards. We'll get back to the fun stuff here in a few minutes. And another big item to consider is charge time. You have a huge thermal mass you're rejecting heat into seasonally. So these systems can take 5 years, even longer, to get fully charged. If you oversize your system, it may never get fully charged. So you just burned a bunch of money up. If you undersize it, it'll get charged right away, but you won't get as much of a seasonal advantage out of it. So if you, hey, I built a system and it's undersized, well, that got me through October, November, and now seasonally I'm kicking on full scale right when I hit the coldest time of the year. Maybe your equipment's good for that, but at least you save some money, right? But charge time's a big one, and it's difficult to calculate, so some people just, hey, let's assume a 5-year charge time. And that's kind of a typical one, which that means your system's going to have to be sized to take full load for 5 years. A little bit about the water equivalent storage. So water has become our baseline. It's got high energy capacity, it can transfer a lot of heat, and so we design everything to water, and then if we want to use a different medium, let's say we found bedrock, and we want to make a giant big ground rock system be our thermal energy storage, so we come out with a water equivalent. I grab numbers for concrete. Concrete's kind of expensive to say, hey, that's going to be my main storage for heat. I'm just going to pour a big thing of concrete. And, well, you might get a lot of heat because it'll never ever cure if you jack that huge of a concrete system. But you also spend a whole lot of money. So as far as its heat capacity, about a quarter of water. Density, twice that of water. So when you're looking at a volume base, you only need double the volume to get the same amount of water equivalent out of the system. So after I go through all those standards, we talk about the huge reservoirs you're going to need, lots of collector area. Just going right back to this system that ASHRAE kind of thinks about. They have huge collector area over here, dumping into a large borehole seasonal reservoir. And that's just kind of nice for your short term. And then a large amount of units on the system. So that's currently how ASHRAE 2016 defines seasonal thermal energy system. That's what they like to talk about. I think we're about due for 2020, if I remember right. If any ASHRAE experts, I think it's every 4 years. So we'll see if the new book has any new systems in it or any new refreshers for small systems. But this is, it's coming back to this is what they have in mind when they have our sizing guidelines. So why solar for seasonal? Our demand, of course, is always there. Or demand is never when the supply is. When it's nice and sunny, we're all feeling great, and then sun goes down and heck. So that makes it a great candidate for our heat source. The technology, equipment, most of it's off the shelf now, so it becomes very cost effective when you're designing them. And a lot of, many of you probably been to Hawaii or other warmer places. You see lots of these daily solar water heaters on top of everybody's roof going across. And those typically are sized off the utilization factor. So most days you're actually exceeding your supply is exceeding your demand. You'll have the water heaters nice and toasty, whatever the 120 degrees you set it at. And then in the meantime, either the system drains out, it just circulates to keep it from boiling off. So you usually have a lot more supply, especially during the summer months, than you have demand. After I'm outside in nice warm place all day, 80 degrees, a hot shower is not the first thing I want when I get home. I want to turn that down to a cold shower and get that 50, 60 degree ground temperature. So it becomes a great place for a load shed for the daily systems, especially when we get into the equipment. A lot of these systems do like a load shed so you don't boil off your water. And relative to other systems, especially when you start talking about molten salt or other phase changing materials, these are simple installations. Simple being relative, as I said. So when you talk about typical residential systems, this looks pretty complex. When you're looking at commercial systems, it's pretty simple. Just have more controls telling more zones or tanks what's going to happen, what's going to do under certain conditions. So right onto our solar collectors. The two primary solar heat collectors are a flat plate and evacuated tube. Flat plate, sun hits it, you have this insulated box, your fluid usually goes right through there, gets nice and toasty, insulation, reduced losses to the environment. An evacuated tube, you have a nice round tube evacuated. The sun comes in, hits an absorber plate, sends the heat to this exchanger, essentially, a thermosiphon heat tube. Those familiar with the pipeline, it's the same principle as all those heat tubes we got on there to keep the permafrost stable. So it'll heat up an intermediary fluid, pressure, temperature, and then your transfer fluid is going to come across this end piece here and get nice and hot and absorb all that heat. So the advantages of a flat plate is it's more efficient. When I say big quotes, I'm more efficient because it's lab and rated efficiency. So maybe that doesn't really apply to real world efficiency because flat plate, the sun comes through, it hits at an angle, you reflect a lot of that light energy, and then seasonally you go up and down. So given the geometry of the evacuated tube, you tend to get more out of it over the term. However, I'm not quite, it's always a debate, you know, especially with installation contractors. Like you just go in, look at a few blogs, and they'll start saying, no way, flat plate's better, blah, 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 and then no way, evacuated tube. So, but the advantage for us in Alaska and other colder climates is evacuated tubes have a very low loss to the environment. It's a vacuum in there, so you don't get convective heat transfer flow or conductive. Any loss is mostly radiative. And so, for example, one of the ones that when we go to my research project said it was 4 degrees outside, and they shot the heat transfer thing with a heat little third temperature sensor. It was producing 90 degrees out of there. So he said, oh, when the project guy was trying to decide what method to go with, he saw that. He says, nope, that's going to be it, because when it's cold outside, I can still get some heat out of it. But again, you do lose your efficiency, especially since you're going through essentially another heat exchange element with that. The fluid inside is generally not subject to freezing at normal temperatures. The companies like to, proprietary fluid is, oh, we're not going to tell you what it is. It's usually methanol or some other type of alcohol like that with a very low freezing point. Comes in pretty handy. So I was like, all the literature is like, oh, our proprietary fluid. And I'm sure they just add something or change it a little bit, but the early ones were methanol. I doubt we've changed a whole lot since then for getting it. CO2 might be. I don't know if that's going to be used in a heat application, but they don't want to publish it. So those were the two primary heat source collectors for solar source collectors. And now for our seasonal storage medium. Water, it's a baseline. That's kind of what everything's sized off of. But it comes with storage problems if you're going to use it in small scale or even in large scale. Large tanks are very expensive. So expensive I can't just find them online, right? They're like, hey, need a quote. But maybe Cold Climate Housing Research out of Fairbanks got a large 15,000 gallon tank donated to them. So hey, that's great for them. If that cost is free, I think that pretty much tells you what your storage medium is going to be. You do have corrosion issues to worry about if you're going to use deionized water or distilled water for that. Concrete's also good. Going back to my water equivalent number of concrete is tough structurally designing. I'm not a structural engineer, but those are the guys who make the big bucks, is the concrete guys. And your biggest pieces of concrete are typically your structural members. So when you want to get a large mass to store energy in, it's going to be a structural member. And I'm going to go to my structural engineer and say, hey, I want to put some tubing inside your structural member. How's that feel? Next to the rebar? We're going to be good with that? My hunch is they're not going to be too happy. So that's one disadvantage. But if you have a large, maybe architectural concrete mass, that could be used. And then sand, also a common construction material. Sand, pit run, D1, I just kind of lumped all those into sand. At a construction site, residential otherwise, you usually have various grades coming in. So most of these sand, your biggest cost usually a lot of times is your transportation cost. So at construction site, it's common, so that's usable. Now, phase change materials, that's the big boys. So that's where if you got money and you really need an application and you go to a phase change material, water's great for going from frozen to liquid in terms of thermal cycles and calculations, but for us, that really makes it tough because you got all that heat in the latent heat of fusion, you got all the energy that you can take advantage of, but now you're going to have either a big storage tank open. It's not really a usable temperature unless you're coupling it with a heat pump. Heat pumps start losing efficiency around 45, 40. 32 is not too bad for a heat pump. Common off-the-shelf heat pumps go down to minus 13 Fahrenheit. So there you have that, but again, I don't know where you're going to get a large reservoir that you can keep, maybe a pool, let it freeze all winter. Not the most practical solution. So real quick, practical solutions. So based off the research we've done, coming into small residential, light commercial design systems that ASHRAE currently doesn't, special care must be taken when designing. Now we'll get into the special care part. So smaller tanks, definitely, they're cheaper. You can run them in series. I would love to take advantage of this idea. I did a presentation on my thesis, and one of the guys I work with was like, hey, I got a whole bunch of plastic drums that are sitting around out in the butte. People have these things all over the place. Can I just string a whole bunch of those in series? It's a great idea. Yeah, you can. I mean, that's fantastic. You can extend your capacity if you need more drums, 5 more drums, or go less, But I can't take credit for that. I can run some numbers and simulations to design for it. Well, also other storage medium, as I mentioned, sand. Because for doing water and residential, it gets tough, especially freezing areas. Glycol starts to get expensive. You're typically running construction fill, D1, sand anyways, somewhere in your site. So you bring another load, 2 more loads, 10 more loads. And then, as I mentioned, freeze prevention, heat transfer fluid. You got to figure out where your temperature is and what you're going to design to. And then this is the part where people kind of cringe, is you're going to need more controls. If you can make up for the upfront design by adding more controls, so you might need, in addition to a thermal energy storage reservoir, you might need a load shed somewhere. If you start rejecting, if you have too small of a system, it's not going to be too hard to get that thing up and above a usable temperature. If you have it coupled to an in-floor system and you get all the way up to 180 degrees in your reservoir, it's really nice having toasty toes on an in-floor radiant system, but it's not nice having toasted toes on an in-floor radiant system. So I hate to see people walk around with foam blocks on their feet just so they can maintain some level of comfort. And the biggest one that we found, insulate your thermal storage reservoir. Insulation is not necessarily the cheapest component. It's not too bad, but protecting it from thermal loss to the environment was key, I think, for these designs. So with that information, going back to how we came to that information, talk about my research I did for the project here at UAA. We had a gentleman who built a home in Palmer. He read in a magazine a guy who had his heat pipe or evacuated tube solar collectors, and he was building his load shed, and he said, what the heck, I'll just put it under my garage. And this guy said, hey, that's a fantastic idea. Let me do that, and contacted UAA, and so we said, hey, that's a great idea. Let's hook up some sensors and do some simulations and see what we can come out with it. So for his system, it's actually designed to be a hybrid seasonal system. So he actively pumps his fluid from his evacuated tube collectors into his garage, and then it passively radiates into the garage space. So that would be the example, the passive system, good for greenhouses or unoccupied spaces. So his living space and his garage space came out to 580 square feet. Not a huge house. So, but it was just him and his wife, and that was his retirement home. So why not? Why not spend some money on it and get some systems I like and have a little fun with it? If that's what you like to do, that's great. Let me know, and we can hook you up with some great ideas. So, and underneath his garage floor, he decided to use the common construction materials coming to a site anyways. Some pit run and some sand. So he had to create a leveling course in his garage floor for his slab on grade. So that's where the sand came in. And then pit run became that's Palmer. So Palmer gold, if you will, the gravel and stuff. So he had a pit not too far from his house, so it was not too expensive for him to get it there. So as mentioned, back up here just a second. So at 580 square feet, going back to our old standards per the original ASHRAE 2016 handbook, he would have needed 1250 to 1870 square feet of collector area. So he would have had to have basically a solar farm somewhere on his property. And he also would have had to have 88,000 to 130,000 cubic feet of water equivalent storage. So that comes up to double that if you're using something like concrete. This amount of space. So it's back to what ASHRAE said, may not be practical or cost effective in a residential setting. I can agree with that under those numbers. So he chose sand. Heat capacity 20-40% of water. 40% end of things is when you really reduce that void fraction, which is compacting. Low void fraction is highly compacted stuff. I say relatively cheap material. Pit run was $5 a ton. Sand came up like $20 a ton, or maybe that was washed D1, washed and graded D1. So it's transportation. That was in the pit cost. The sand transportation becomes a huge deal with gravel pit run. I know that's typically why they called it Palmer Gold. Is you're like, oh hey, I'm going to order 20 tons of pit run, and then your transportation cost is exceeding your material costs if you're far enough away from the site. But the nice thing about sand is it can take any shape you like. So it's not like you're constrained to whatever the tank manufacturer can make to meet those codes. And especially when you go from off-the-shelf tanks, the 500, 2,000 gallons you see all the way north in Fairbanks, Delta Junction, where everybody uses heating oil, you see, okay, they have a lot of these tanks that are practical, but then when you start getting into these large systems, now you're going to have to get a special made tank. Incredibly expensive, and you're stuck with these sizes. And especially so for him, the flexibility was great. He's just got a foundation wall there, and he just filled that up. So that becomes really handy, especially for us with, crawl spaces, strange structural design. So it's nice to be able to hide it under the structural itself. And then the good thing about it is the durability. So if your tank for water gets a leak, you have potential of losing 5 years of stored heat. And you have corrosion issues. This sand is gonna be great. He put a vapor barrier around it to prevent any migrating water from coming through the thing. And given 20 years, I'm sure there's gonna be lots of little holes, but you're not gonna get huge amounts of water flowing through this thing. So it's probably gonna be there for a very long time. As long as I think the point of failure would be the PEX tubes on this system. So we looked at the thermal properties of his sand. We are way down there in the 0.6 to 0.7 specific heat for the different materials he came up with. We kind of talked to him a little bit about how he installed it. He says, yeah, I kind of compacted it. No, wait, I brought in a thing and compacted it. And so we weren't able to get a good compaction method on it. So we kind of tested it at we knew the ratios of what was in there. So we tested it with compaction of the ratios. We used, down here in the civils lab, I thought this was going to take a long time to get these numbers, but the civils lab has a probe. Oh yeah, you just stick it in the soil and it gives you your properties. And I was like, nice, I just saved a month off of my research that I had planned. So I wish I would have used that time wisely. So we say pit run outperforms sand. Oh, so on the bottom here we have water, that we put water in it. Pit run wouldn't hold a lot of water, but it did use that water better. Our assumption is from the random size of material in there that it creates a lot less void fraction. It wouldn't hold that water, but now you have all that space is water as opposed to a fine sand leveling material. You get a lot of space in there, and even when you fill it with water, you compact it, you still have a lot of air in there. So, but when we say outperformed, when you're doing dry materials, because I don't think you can really plan on having a wet sand thermal reservoir to last and stay with that same moisture content over 20 years. I don't think that's a good practice in design. I think we should stick with assuming dry material on future design. So yeah, it outperformed. It was 0.7 instead of 0.6 kilojoules. Whoop-de-doo. But it is super cheap, so why not get it? Here's real quick our combined thermal properties of all this. And when we use the ratios that we had, said we got 0.668, no big deal. Compacted 0.74. It's not a widespread for these materials. The moisture content was the biggest factor. We knew we didn't have moisture content in there, but I wanted that data anyways. And so now we'll go up to the geometry of it. Here's quick his garage floor plan. 21 by 27 roughly, 30 inches of material, 8 inches of insulation on the bottom. And here's the foundation walls. 8 inches of insulation on the inside, 8-inch CMU wall, poured concrete wall, 8 inches of insulation on the outside. See some faces in there. That much insulation probably set them back a ton of money. That didn't. So this is an atypical design, but he went to a school roofing job site where they're taking off the old roof insulation. And he just said, hey guys, can I have some of that? And they said, yeah, sure, take it. So he loaded his trailer up with the foam board, and he says, man, I got more than I thought I did. So he just kept using it. I was like, he's way more resourceful than I am. So we came up to almost 1,900 cubic feet of storage sand. That came out to 47% water equivalent, about 50%. So we're getting close to concrete as well. And so our water equivalent was 878 cubic feet, or almost 6,600 gallons. 6,600 gallons is, as far as I could do off a quick internet search, specialty tank area. Or you can just get a lot of 55-gallon drums and put them in your crawl space. They'll fit in my crawl space, so that's kind of cool. I can actually do that as a remodel. Unfortunately, I'm forced air, which makes it a little difficult from that perspective. But just to go out and buy that tank before you even start filling it in, if you decide to use solution to prevent freezing or to do deionized water, like to think water's free. Distilled water at Fred Meyer is not free, like $1 a gallon. I'm sure in the commercial world it's much cheaper when you're buying those systems. So for his solar collectors, he used evacuated tube. As I mentioned before, he evaluated several different ones, but he said, nope, I'm going with those. Sundecyto 5 Texas 16 was the model number. Is a rated, so the stagnation temperature on evacuated tube solar collector, it's if you have a design condition with the sun perpendicular onto the collector, into the manifold, if there was no water flowing, that tip would read 430 degrees out of the factory. These are lab conditions, but that's pretty hot. And that's what's really nice about that is when you're using thermal models, the difference in the delta T is rated, gets you the more work out of it. It's more, I know heat's heat, but I like to think of it as better heat. So it's more useful, especially in your direct applications. So if you couple it with, yeah, go ahead. The question was what were the cost of the evacuated heat tubes? And the engineered answer is, I don't know. He actually had forgotten because he bought them with a friend in a bulk buy 10 years before they were installed. He just said, I don't know, maybe 1,000, maybe 2, nah, I don't remember. So it was, they're pretty common though. They're very off the shelf. You can go on the internet, do a quick web search, and come up with prices. For those systems, he dropped a couple, so he said they're pretty durable because nothing broke, but knowing shipping in Alaska, I would be hesitant to buy them online and have them shipped up. Just me personally, from my experience, when something shows up and just shaking glass inside of there. So I imagine our local renewable energy shops would buy them, ship them up for you, so that way they can take the hit for any shipping damage. But from the data plate, it was just slightly over 80 square feet of collector area. And here is so they come with a published efficiency curve. They had to start giving data on their lab rated BTU output, but it was hard data to do based on, you have to do flow rate is the other thing with these, is while your flat plates, they're very easy to design, and we as engineers tend to like numbers we can rely on and not have to guesstimate at all. So flat plates are the dominant method for solar heating right now. Evacuated tubes are picking up, but the rated efficiency curves are based on your how much wattage per square meter is hitting it and the atmospheric temperature. So this kind of tells you your efficiency of your absorber collecting it, and that's the heat transfer into the fluid. So while it seems kind of low at 50% compared to some other methods, it is nice high temperature fluid. So you'll get more efficiency out of your thermal storage as a heat exchanger because you'll be coming out of it with a much higher temperature. So here's the control setup. Okay, I'm not going to try and mess with the laser pointer here. So here's up here is your evacuated tubes. Runs through heat exchanger. So this is the domestic hot water supply. Keep the system separate. And then there's our sand bed, which it was a 2-tank controller. So we just said, hey, tank 2 is our sand bed. And then tank 1 is our domestic water heater. If tank 1 is not calling for heat, and that's 12 degrees warmer than this, send heat there. That's his load shed, so he would not have to worry about burning off because he had a glycol solution in there to keep it from freezing. So he was worried about getting that too hot, burning off the glycol, which creates all sorts of fun issues when you start boiling glycol solutions. And that's off-the-shelf Home Depot, Lowe's type glycol system. I know there's a company out of Fairbanks that does their own glycol mixes, and they have glycols that are rated up to 300 degrees Fahrenheit, which might be a great application for. But when you start buying those specialty things, I didn't ask how much. I was just like, hey, that's cool engineering data, but typically if you're going to go and say, hey, I need 5 gallons of this really high-end glycol, they might just send you away or tell you, oh, that's fine, $10,000. So but there are things out there that can help reduce the risk of boiling it off and ruining your glycol with having that break down. If you get a bunch of people together on a bulk buy, or you have the company for installing these, yeah, you can do that. So here is our measured temperature profile. So red, hot in, cool is our outlet temperature. Apologize, it is in Celsius. So when I'm doing the research, it's so much easier to work in standard units. But when I come back to try and relate to people, I got to convert it back to Fahrenheit, because most people still that register what that is. So here, these high temperatures at the beginning is when we were messing with the pump. So he had a fancy Grundfos multi-speed, multi-pressure pump with different controls on it. We were like, hey, let's start playing with this. We're like kids. so we ended up getting some briefly over boiling temperature, almost 100 degree Celsius, so 212 Fahrenheit fluid out of there. And so we decided to quit playing with it and just turn it on a good, comfortable setting. And then it kind of ran nice and steady. You'll see here February, March, 50 degrees Celsius, almost 100 degree Fahrenheit water coming out of that thing. So at those kind of temperatures, especially when you get into radiant floor, you might almost couple the systems together. So not even go to the thermal storage. However, radiant floor, I understand you want a lot more control over the temperature than, hey, I'm just going to shove 100 degree Fahrenheit water through it. So what this equates to is we are getting a delta T in Fahrenheit of 16 to 27 degrees about out of our heat exchanger. So that was the temperature range we're seeing, well above the 10 degrees recommended by ASHRAE. For the heat exchanger profile, we had really good numbers, a lot of high efficiency for that. I brought my thesis for you. There's also a copy here in the library and with the mechanical engineering department if you would like to get more into the details of that particular system. And here are all of our temperature sensors that we put into the sand bed and what they read. So they're all really close together within a couple degrees Celsius. Little comment on this little dip, the purple dip there in March, is we had a cold snap in March, and simultaneously the homeowner accidentally left the side door open on his garage. So what was really cool about that is the surface got really cold, but the core and the rest of the temperature profile just didn't matter. There's so much mass there, thermal mass, that its kind of capacitance factor to react is just very slow. So we collected a bunch of data. I'll talk briefly about the numerical simulation part of this. We did this in Transys, Transient System Solver. I think it's currently held and managed by the University of Wisconsin. It was developed in Fortran. I don't know how to program Fortran, but somebody might. And it still uses a Fortran background programming language, but they've at least converted it to a GUI interface. What's great about this is you can, if you knew how to program Fortran and transfer it into Transys, is you're allowed to own that property. University of Wisconsin wants people to develop items for this. However, you still got to buy this initial software. So for us, this is the rock bed storage. Real quick on the rock bed storage, the Transys rock bed storage is a uniform rock bed with the fluid going in contact with the rocks. So it assumes tennis ball to basketball size rocks. Nice, spherical, easy, that the fluid transfers through and is in direct contact with. The simulation component is very different than our reality of what we used, but we found it works really well for large, thin systems. So if you have a depth that's very relatively low compared to your length and width, it seems to work well for that kind of simulation. So since it's a hybrid system, we added a convective factor for heat loss into that rock bed system rather than build a house with demand. That greatly helped our simulation along. So here we go where we take our recorded data and lay it over the simulated data. This is our ambient weather. Now with ASHRAE as well as Transys, we use the TMY2 file. It's kind of the danger of these simulation systems and the calculations is they are for an average year. They've taken, Transys taken 30 years of weather data, cut out all the extremes. So as you can see, we had a cold snap where we got down to minus 20 equivalent Fahrenheit, and we stayed well below minus 15 for a couple weeks in March. Transys doesn't consider that. They've taken an average weather data, and even ASHRAE data doesn't do that. For their published weather data, their standard design temperatures are based on average years. Every single year is anything but average. So when you compile them over 30 years, you can look at an average year, but every single year seems to have one extreme somewhere. So that's a design consideration we need to account for. Thermal energy storage is a great way to actually account for that extreme. If you have a thermal base that you can draw from to help cool or heat during those extremes, that's one way you can use these systems. So here's so the previous data was our ambient weather, and this is our 14-week simulation. So we've done our simulations in blue. The experiment is in recorded data is in red. And you can see that we follow the curve really well, especially when you account for an average year versus the extremes we saw. So we looked at that and we said, hey, that's fantastic. Let's go with that. And after we did that, we wanted to do a 5-year seasonal because I was not going to wait 5 years to get my master's degree. So luckily I got to do a simulated seasonal thing. If I took 5 years to do my master's degree, I might as well just live here, I think. Let's see. So you can see, here's our first year in our simulation. We become charged in our first year. As I mentioned before, these systems can take up to 5 years to charge. So we're already in a pretty well cyclic pattern with our highs and our lows in a passive environment. So what that equated to is our space's maximum estimated ambient temperature, about 77 degrees Fahrenheit. Its minimum in the cold time is 52, which is where my dad always wanted to keep the thermostat growing up. And so we've come to the conclusion that this system, specific system, was good, acceptable for a non-occupied location. So I want to bring those results back to where we started comparing it to what ASHRAE recommends. So we had 0.15 square foot per unit floor area, just under 10 feet of cubic feet water equivalent storage area, and successfully did extended freezing periods. The homeowner still has a system set up. He's still using it since it's a hybrid system that passively radiates into the environment. He keeps his garage door open most of the summer because it starts to get a little too hot for him to work in it. So it's got a lot of like shop space. But he still keeps it going. He hasn't had to turn on any heat into his garage. Rough cost estimates. So good cost estimates are plus or minus 30% at best, in my experience. So we really shot from the hip in 10 to 20 grand. I prefer to do heat equations and heat analysis and cost analysis. If we find somebody, maybe we can find a student working on a project that wants to do our cost estimate because all the data it's out there. It's really easy. The equipment's simple. You can just grab it together and then do analysis over time. I just work and have kids, so I haven't found that time or really desire because, like I said, I'd rather do the heat analysis side of it, the fun stuff, the engineering side. Not that cost is not engineering. Sorry, I didn't mean to downplay that at all. But also, kind of, we've decided undersize is better than oversize. Supplemental system, if you undersize it, you will at least get to use it. So a quick note on this. This system is for that house only. So we don't have general design guidelines yet. So I know, I wish we did. I wish I could give you something better. But right now, for your design guidelines like they have for large commercial installations, we just don't have those. So given that data, we are confident that if that system was a fully active insulated system, we could easily have satisfied 50-80% of his needs per the ASHRAE standard, if not 100%. But his house was his personal, it's a very unique house, highly insulated. So it's, like I said, that system's good for that system, or those parameters are good for that system only. So where we're currently going with the research is we're trying to develop a transist component that more closely matches a sand bed heat exchanger. So that's the Fortran I talked about, the programming language, and then of course you got to get your basic heat equations and transfer them to something that's programmable. And then we can set up experimental verification, check out that problem. Once we have the Fortran component, we can do all the parameters we want to start optimizing into something that's good for real world situations. The other option is you find backyard tinkerers, people who have money and want to play with these systems, and then we start setting up test case, record data, and see where that lines us up. So we're always looking for test cases. If anybody volunteers, anybody? And research at larger universities with a lot more money is going into the heat exchange material. So that's going into phase changing. Like I mentioned, paraffins, waxes, they're looking at those. They phase change at temperatures we like, but they don't have hardly any energy in that phase change. So they're looking at ways to make those kind of materials better and actually store a significant amount of latent heat diffusion. Nice. And that is it for this presentation. Any questions? Go ahead. So the question was to better clarify evacuated tube solar collectors. And give me a second, I'll get back to the unit. So yes, we have a glass tube completely evacuated. The sun heats typically a copper tube that's filled with a heat transfer medium like methanol. And this will boil up, create vapor, heat, pressure right there, and then the glycol, these will be installed in a manifold configuration, and the glycol or water solution will flow right across the bulb and pick up that heat. So in this particular one, on the front of the house, those 32 glass tubes are the evacuated tubes, and the pipe on top of it is where the fluid runs in the manifold and picks up the heat. So it is this configuration. You can't do parallel. This configuration is series. So yeah, pick up heat here, pick up more, drop out. If he decided to go with 64, he's probably boiling on one end and on that sort of setup because he's going to pick up a lot of heat. Cool. Any more questions?
What was on his rooftop?
Those were photovoltaic panels. So he had 13 of them, and photovoltaic, we would put it at 60 degrees for optimum electricity. The evacuated tube, you need a tilt to them, so the fluid will condense, or the vapor will condense to fluid at the top through the manifold. So they generally, you don't want them tilted too far back. 60 degrees is fine for us. For people closer to the equator, that may not be an acceptable solution. So for them, you may say, hey, evacuated tube is better. And when people say what's better, evacuated tube or flat plate, we get to say the very common engineering saying, well, that depends. So,
Does it have to have southern orientation?
it's preferred, yes. No, it doesn't. If you have it set up on its own, it doesn't really matter if you don't have a house or anything blocking the light. We did find it was nice, even when it was cold, it would get a lot of, in the wintertime, get diffused radiation from the white snow. So you'd see higher temperatures after a clean snow. So you could go out there and brush them off with a broom.
How big was this sandbag?
30 inches combined?
Did they have that filled with water?
No. It was half pit run, half fine sand, and then a 4-inch slab on top.
Couldn't you just repetitively keep it filled with water?
Every time you do that, you add a new, if you weren't adding a lot of water, yes. So if you keep adding it in, you're trying to boil a pot of water while throwing in a cup, taking out a cup, adding a cup.
Since you can charge it the first year.
Yeah, if you charge it up, it would be a good way to change your capacity. Oh, sorry. The question was could you could you refill the sand bed with water so you can increase its capacity? And the answer is yes. As long as you were doing small amounts of water, once the system was charged, and if you saw it was losing capacity, you could add water to it, as long as you weren't adding enough to greatly. If you were adding too much mass, you'd have to start all over from the charging perspective. Oh, yes?
Did you instrument the solar side of that, or just the bed side?
The solar side, he did instrument that. I don't have the data readily available. I just know I had the solar capacity available if you'd like to know it. But his inverter had everything metered for the solar side. Oh yeah. The solar thermal output temperature, it went straight into the sand bed. So that would be the red line. Yep. Yeah, it's tied to the bed and domestic hot water. So he's not using it for his space heating.
So when you had a glycol mixture rotating around or circulating around, what was its boiling point? Because in an event of a power outage in the summer, would that damage the system?
Yes. Back to control. Repeating the question is, in the event of a power outage, would the glycol in the manifold boil off and damage the system? And the answer is definitely yes. It would happen if there was a power outage. If you had solar batteries, it could mitigate. The other thing is a lot of these systems are designed with it empties out into a reservoir when the system's not being used. So they actually have a system tilted, and it opens a valve and fills the system with air when it's not being used and dumps into a reservoir. That's one of the control strategies to think about when doing that. And the other thing, of course, is it's dry. Its stagnation temperature is 430 degrees. So if you had a mixture that would do that, which we have some expensive Thermanol DuPont solutions, but I don't recommend that in residential usage. Thank you, everybody, for listening to me. Had a really good turnout. Thanks. Still plenty of food in back. What they do with it. Oh, okay, nice. So it's
Card or